Yeah. Hello, guys. Good evening, everyone. Welcome back to one more 360DigiTMG's domain analytics session. In this session, we are discussing the healthcare analytics. It's been over 6 days. We've been discussing different use cases. In the very first class, we have discussed about what are the applications when it comes to domain, healthcare analytics. How we can apply the machine learning algorithm when it comes to healthcare. And we have seen what are the algorithms we'll be having, like supervised, unsupervised, all those things, in machine learning. Then we have discussed about how we can clean the data. How we can clean the data when it comes to text and when we have a data frame. So we have discussed most of the pre-processing techniques. How can we clean the data and all? And then we have came to the unsupervised learning. In that unsupervised learning, we have taken one use case in K-means algorithm, and then we have taken supervised learning. In that case, we have taken one more use case predicting diabetes, and then we have used one more use case, predicting whether the particular person having the benign or malignant. Today we will be discussing about the simple linear regression. It is also one of the supervised learning. What is supervised learning? We will be having labeled data. Labeled data. So it is also supervised learning. So we'll see one use case at the end of the session, how we can apply this simple linear regression when it comes to healthcare analytics. So let's look at the agenda of this session. So first, we will be discussing about what is regression analysis. And we will see what is linear model, what is correlation analysis, and equation of straight line. So whole regression is using this equation of straight line also only. So we'll see how we can apply the regression when it comes to equation of straight line. What is simple linear regression? What are the transformation techniques and when we will be using the transformation? And what is bias and variance? And we will be discussing one business use case. So this is the agenda for today's class. Without wasting any time, let's get into the session. So regression, what is regression, guys? Regression is you study the relation between the two variables. Let's say when it comes to classification, what we have? X1, X2, we have different inputs, and then we have output. Obviously, it is a supervised learning, so we should have a labeled data. Whenever output is categorical means that could be yes or no, something like that. Whenever you have something like that, we will be going for classification. Whenever you have a target column that is the categorical, if it is in categorical form, we will be going for classification. But when you have target column in continuous form, whenever you have a target column in continuous form, we will be using the regression. We will be using the regression. What is regression analysis? We simply studying the relation between the two variables, that is input variable and output variable. So whatever the variation we are doing in input variable, how we can output variable is capturing, that we will be seeing when it comes to simple linear regression. And when it comes to simple linear regression, we have some rules. Whichever the columns that we are using, in our in simple linear regression, it should have a correlation with output. Whatever the input columns we are using, it should have a correlation with output. That is why. So if it is whichever the input variables we will be using, if it is in the form of continuous, if it is in the form of continuous, you can take as it is, and output obviously will be having in continuous form. If it is continuous form, you can directly take it that input and you can go for model. But if it is in the form of categorical, whatever the input we are taking in simple linear regression, if it is in categorical, you have to convert that categorical input into numerical. Whenever you have a input variable is the categorical, in that case you have to convert into numerical. We'll be having different techniques like encoding. Encoding techniques will be having something like dummy variables, one-hot encoding, label encoder, something like that. We'll be having different techniques to convert all the categorical values into numerical. So it is a regression analysis is simply the study the relation between the two variables. It is one input and output. When it comes to simple linear regression, we can use simple linear regression if both the dependent variable and independent variables are numerical. You should be having both are in the form of numerics, like we discussed earlier. If you have any categorical, you are supposed to convert that into numerical. And we should be having dependency or the correlation in between dependent and independent variable. What is dependent? That is the output. What is independent? That is the input variable. So how are we going to calculate the correlation between the two? Whether it is in between independent variable or the dependent variable, how are we going to do the correlation? You can use scatter plot. You can take input variables on x-axis and output variables on y-axis, and you can simply plot that scatter plot. If you are having the linear relation, if we are increasing the IQ, and also here we are taking sample inputs. Whenever you are increasing our IQ, the income is also increasing. In that case, you can say it has linear relationship. Whenever you increase x, y is also increasing. In that case, you can say it has a linear relationship. Here we have taken body percentage, body fat percentage, chance of the heart failure. Whenever body fat is decreasing, the chances of having the heart failure is decreased. And then at one point, even though the body fat percentage is increasing, first what happened? Whenever we are increasing the body fat, it is keep decreasing. When the body fat is increased, after some point, it is heart, chances of heart failure is also increases. It is having it is not simple linear relations we have. Here we don't have a relationship of linear. Here we have exponential. Here we have an exponential linear relationship. Based on that, we will be applying the model. Whether we have a linear relationship or we have different relationship. Based on that, we will be applying the linear regression. So how can we say we have a strong correlation? How can we say we have a not that strong, moderate or no relationship at all? correlation at all. How can we say that? Just by looking at the scatter plot only. You have to take one input on x-axis, and you have to take one another input on y-axis, and you have to see the linear relationship. If it is in just one line, in that case you can say it is a strong correlation. If you are having something like this, you can say it is moderate. So whenever you are increasing the x value, and if the y value is, whenever you are increasing x value, if y value is also increasing, in that case you can say it is a positive relationship. If it is in just near to one line, in that case you can say positive strong relationship, positive strong correlation. Whenever the same, if it is positive, but it is not that strong, it is moderate positive correlation. It is not a strong, but it is moderate positive correlation, but it is increasing when you increase any one of these. So it is positive, but not strong. Here we don't have any correlation. Here we don't have any correlation. Here, whenever you are increasing the y, and it is decreasing. In this case, we can call it as a negatively strong. Negative strong relation. So here we don't really have just linear. So we can say it is a negative but moderate correlation. Here you have linear. In that case, you can say negative strong. Here we don't have any linear relationship. We have a curvilinear relationship. It is a curvilinear relationship. Whenever one value is increased, when you have increasing the y, x is also increased, and it is linear. In that case, it is a strong. If it is decreasing and it is a linear, in that case, you can say it is a strong negative. And in this case, it is a linear, so curvilinear. So by just looking at the scatter plot, it is a scatter plot or scatter diagram, you can say. By using the scatter diagram, we can plot whether it is positive correlation or it is a negative correlation. Quantify this relationship also using the correlation coefficient. You can quantify how much correlation we have. Instead of just going by picture, we can quantify how much correlation we have using the correlation coefficient function that will be see in the code. But just remember, we can quantify the correlation. So you might be having an idea about one linear line or straight line equation. Y is equal to mx plus c. The same way we will be having the a line equation when it comes to linear equation. That is y is equal to a plus bx plus. Here y is the output variable and a is the intercept and b is the coefficient and x is the input. And here we have e is the error term. Here e is the error term. So whenever you are taking, let's say you are taking just one input variables and one output variables. It is a simple linear equation and it is a represent of simple linear equation. So whenever you are increasing x, here we will be having x and the b is the coefficient of independent variable x. And here we will be having intercept. How we going to find out the intercept? We'll see in the coding. Using this equation, we are predicting the y. What is error term here? But whichever the value you are getting, after prediction, predicted value and the actual value, whatever the value will be having in data frame. Predicted value and actual value, it will become the error term. This can be so we can calculate the error term just by using the predicted value and the actual value. So I've told you, right, we can quantify the correlation, how much correlation we have. That we can use correlation coefficient. Here the correlation will be in between -1, ranges from -1 to +1. So whenever you have a correlation value that is -1, you can say it is strongly correlated. It is a strongly correlated, but in a negative way. You can say something like this: strongly correlated, but in a negative. Whenever you have positive value 1, in that can say strongly correlated in a positive way. You'll be having data point something like that, just one line. I mean, along the linear line. Whenever you have -1, it is strongly correlated, but in negative, and it is strongly correlated in a positive. Here you can see R value. You can the correlation will be denoted by small. So here 0.4. Whenever you have a correlation value is 0. It will look like this. When there is no correlation in between the two columns, here you can say in y-axis we have taken something, x-axis we have taken some feature. When it comes to simple linear regression, it is x and y, and if you are taking any other variable, in that case you can take x. So here you can say you have a 0.4 correlation in a positive way. Here we don't have any correlation. Here we have a correlation in a negative way. Correlation in a negative way. You can also call, whenever you have a positive correlation, it is 1, and that is a perfect positive correlation. And when you have -1, it is a perfect negative, because that is the maximum we'll be having. -1 to +1 is the range for correlation coefficient. And whenever the R value is equal to 0, it is a no linear relation. You won't have any relation in between those columns, or input feature or output feature, whichever the feature you are taking on the axis. So how does this simple linear regression works? Based on which technique? Simple linear regression. How does it work? So whenever you have, based on the, whenever you have just two, x and y, so you'll be having data points. These are your all data points. What we will be doing, using the simple linear regression, we will be taking one line, that is a regression line. So we'll be drawing one regression line, and we'll check how this is a predictor line. Using the linear regression prediction, we'll be forming one prediction line, and then we'll check how far those data points from the predicted line. How far those from the predicted line, and we'll check how much error we are getting. How much error we are getting. something like that we will be doing multiple times. We will be doing the multiple regression line we'll be drawing, and each time we'll be checking how much difference we have. Each time we are checking how much difference we have. Whenever the error term becomes the lowest, whenever the error term becomes lowest, you can say that is the best regression line. You can say that is the best regression line. So it is called the ordinary least squares. It is called ordinary least squares. It is a common technique for estimating coefficients of linear regression equation, which describe the relation between one or more independent quantitative variable and dependent variable. Here we are taking the simple linear regressions. In that case, we will be having just one independent variable and one dependent variable. Whenever you are talking about simple linear regression, we will be having just one independent variable, that is input, or you can say feature. We have different name when it comes to input. Dependent variable will be having output or label. So ordinary least square is checking the linear regression equation which describe the relation between one or more independent quantities. When it comes to multiple linear regression, will be having multiple. Simple linear regression will be having just one line. It is an equation to that particular line. Here we will be having constant term. Here we have coefficient. We have a coefficient. Like that, we will be deciding the best regression line. Deciding the best regression line. It is not just line. We are not taking just one line. We are doing multiple iteration. Wherever this error term is the least, that only we will be taking the best regression line, or we can say best fit. So in order to evaluate that particular model that you are getting, is it best fit or not? How are we going to decide that? Based on R square. R square we can also call it as a coefficient of determination. It represents in percentage. The values ranges from 0 to 1. Whenever you are having the values near to 0, in that case you can say whatever the relation that you have in independent variable, you are not able to capture exactly in output. R square is also known as a coefficient of determination. It represents percentage variation in output. Dependent variable explained by the input variable. Whatever the variation we are having in the input variable, that should be represented in the output as well. So whatever the variation we have in the input, that we should capture in the output. How much it is capturing, that we will know using the R square. You can say R square value, or you can say R2 value. So higher the R square value, the better the model fits your data. So whenever you are having the highest R square value, you can say, yeah, the model that you have built is the best model, you can say. R2 square is always between the 0 and 100. It is in between 0 to 100. The higher the R square value, you'll be having the best fit. So if it is if R square, that particular R square is between 0.65 and 0.8, it is called moderate correlation. Whenever you have R square value in between 0 to 0.65, that is 65% to 0.8, that is 80%. In that case, you can say it is a moderate correlation. If you have R square value, that is R2 value is greater than 0.8, in that case you can say it is a strong correlation. Like we have discussed in the correlation, the same way R square. It is looking the correlation between the input variable and output variable, right? Input variable and output variable. Whenever you have a R square value greater than 80 or 0.8%, you will be getting R square in 0.8 only, and that then you will be multiplied with 100%, so that you can get in percentage. 80%, you can say, if it is greater than 80%, you can say it is a strong correlation. So mathematically, the variation, it is predicted value and it is actual value. It is a predicted value, it is actual value, and it is predicted value. Combining will be taking the measure of total variation. Combiningly, we will be taking as a measure of total variation. And R score is SSR by SST. Measure of total variation. Like that, we will be calculating the R square value. So the more the R square value, the best the model is yours. The more the R square value, the better model fits your data. So how are we going to check those values? We will see in coding. Before that, you should know what is the prediction and confidence interval. Prediction interval and confidence interval. So what is prediction interval? A range that's a single new observation is likely to fall. So whatever the new observation that you are taking, if it might fall in this prediction interval. It might fall in this prediction interval. But when it comes to confidence interval, it should, whatever the range that mean response that you are taking, it should fall in the confidence interval. Prediction, it might fall, but when it comes to confidence interval, it should fall in that particular interval. So this is a difference you have to. So whenever the input column, once the model is built, whichever the input that you are taking, if you are getting in a prediction interval range, in that case you might get good accuracy, you might not get, you don't know. But if it is in, but if it falls in the confidence interval, the accuracy that you are getting, that could be high, max you can say. Whatever the new observation, if it is falls under the confidence interval, in that case the model will be giving the best output or best prediction. That is the confidence interval and prediction interval. So yeah, when we will be going for regression or simple linear regression, in regression we have different, that is one simple linear regression that I have discussed in the earlier, that is multiple linear regression. One is simple linear regression, one is multiple linear regression. What is the difference between these? You will be having just one input when it comes to simple linear regression. You will be having just multiple inputs. When it comes to multiple linear regression, the name itself says you will be having multiple inputs. So whenever y is continuous, and x is single and continuous, and you have a x single means just one input and it is continuous, then you can simply go for simple linear regression. If you have y is continuous and you have x single and continuous, in that case you can directly go for simple linear regression. And when it comes to same, but we have here discrete as an input. Y is continuous, and X single and discrete as an input. Discrete means categorical. In that case, what you have to do? You have to convert that into numerical. You have to convert that into numerical using the dummy variable or some other encoding techniques. You have to convert that into numerical. Then you can go for simple linear regression. Whenever you have just single and continuous, you can simply go for simple linear regression. But if you are having the single and that is discrete, in that case, you have to convert into dummy variable. You have to go for dummy variable. So error term you have seen, right? Y is equal to beta naught plus beta 1x into. This is the error term. So whenever you are calculating the error term of predicted and actual input, the mean of these values, errors, you can say the mean of error is always equal to 0. The mean of the errors, the whole errors, whatever the model you are predicting, or if you are finding the difference between predicted and actual, if you calculate the mean of those, it will always equal to 0. In that case, what you have to do? We have to go for root mean square. So instead of simply considering the mean, we are squaring it. We are scoring the difference or the error. We are scoring the error and then we are combining it. Whenever you do this the squaring, in that case, let's say you have a 3 error. In order to avoid that mean value is equal to 0, you are simply squaring. In that case, it will become none. But is it the actual value that we are having? No, right? So actual value is 3. In that case, what you have to do? You have to root square. You have to apply root square. So it will become mean. So whenever we are using the evaluation matrix, these are called evaluation matrix for regression. In evaluation matrix, we will be taking root mean square error. That is RMSE. We will be taking root mean square error. That is the root mean square error. Evaluation matrix for regression is what? Root mean square error, RMS. Yeah, that is about the simple linear regression. How it is working, how we are predicting that regression line, which one we are considering, what are the rules, what are the rules when it comes to input columns and output columns we have seen. So here we have one use case scenario. The problem statement when it comes to this use cases, studies has shown that individual with excess adipose tissue that in the abdominal region have a higher risk of cardiovascular diseases. Whenever you have a excess adipose tissue, that is kind of fat. Whenever you have a excess adipose tissue, then you will be having a high risk of having the cardiovascular diseases. So in order to calculate how much you have, in order to calculate how much fat or adipose tissue you have, we will be going for CT scan. That is computer tomography. You will be going for CT scan. That is computer tomography. But the problem with CT scan is many physicians do not have access to that technology. When it comes to rural areas, you won't be having access to this kind of technology. And one more thing, whenever you use the CT scan, scan continuously, the radiation that comes from the CT scan, it will suppress the immune system of the body. The CT scan, if you go for a CT scan, it will, whatever the radiation coming from that CT scan, it will suppress the immune system of the body. So it is not recommended to go for CT scan, even do X-rays. I mean, whenever you are going for X-ray, they will tell you to not to go for not more than 2 times in a year, something like that. So it will definitely affect your body or the tissues that you have in your body, because it is radiation. So what is the objective of our problem? I mean, the business objective of this use case, you have to come up with, you have to develop a simple yet reasonably accurate way to predict the adipose tissue area that can be easily available, and it is risk-free and inexpensive. When it comes to CT scan, it will be costing around 5,000, minimum 5,000 to 50,000 rupees. So it is very costly. So you should come up with a reasonably accurate way to predict the adipose tissue area. This is where we are building one simple linear regression. In that, what we are taking? We are taking input as a waist circumference. We are taking waist circumference as input and adipose tissues as output. So obviously it is a what? Supervised learning. So we have to have one label. Here label is adipose tissue, and we'll be having waist as an input variable, or you can say input feature. So this is the problem statement. We have to come up with one model that can calculate the reasonably accurate to predict the adipose tissue area. Yeah, we'll look into that. We'll look into the code. So for that, we have to import the pandas. Why we are importing pandas? In order to do manipulation, data manipulation. What is this data manipulation? We have seen in the last class. Whatever the changes that you want to make, all will be possible using the pandas data frame. Whatever the changes you want to make, it is all possible using the pandas data frame. And whatever the mathematical calculation you want to make, if you want to do some mathematical calculation, in that case, you have to import the NumPy library. Import the NumPy library. So we'll be having some historical data regarding the waist circumference and adipose tissue. We'll be having some historical data regarding the waist circumference and adipose tissue. We'll be simply training the model based on that. We'll be training the model based on this, and we'll try to predict the adipose tissue with the model that we have built. Yeah. Let's import the data set. Just some advice. Import the partners. So this is the data frame will be having. In this data frame, we will be having one waist column, waist. It is a waist circumference, and we have a adipose tissue. When you have a waist size is equal to 74.4, 74.5, 74.75, in that case, we'll be having 25.72 adipose tissue. So this is the data frame we'll be having. So we'll be training based on this data frame only. We'll be having how much? 109 data and 2 columns. So before that, see all these things, whatever the model that we are building, first we have to go for pre-processing. All the pre-processing, but we are just building the base model. So I know that there is no, don't need to do pre-processing since it is a clean data. But if you are going for the simple linear regression, please do the pre-processing. If you are taking any data frame or data set, do the pre-processing and you can proceed. So here I've taken the data frame in that we don't have any outliers. So I'm simply going for. So describe what are descriptive. It will simply give you what are the minimum values, maximum values, and how many values are present in between 25 percentile, 50 percentile, and 75 percentile, and what is the maximum value. It will give you. Then I'm going for plot. That is a matplotlib. Matplotlib, we are importing the matplotlib in order to do the visualization. In order to do the visualization. For visualization, we'll be using matplotlib, and we have one more, that is Seaborn as well. Seaborn. We can use Seaborn as well for visualization. Imported. So I'm going for bar plot. For which adipose tissue? Yeah, this is the bar plot we have. You can say how much adipose tissue, how many people will be having. It doesn't give you exact number. Simply go for histogram. It will give you the good result compared to that. See how many people have the range. So when you observe the data frame, is it normal? Yes. It is slightly right skewed, right? So it is not a normal. So whenever you are building a model, make sure that whatever the data frame that you are taking, whatever the input column or feature, whatever it is a continuous, make sure it is a normal. If it is not normal, we will be having different transformation techniques. Different transformation techniques you can apply and you can make them normal. And then we are going for box plot and checking whether we have any outliers. in 80, that is adipose tissue column, will be having any outliers or not, we'll check. See, it is a box plot. Do we have any outliers? No. So it is a clean data. So I'm checking same for bar plot for both adipose tissue and the waist. I'm checking now for the waist column. And you can see the histogram plot. These are univariate plot as. Can you see whether it is normal or not? Normal or not? It is not normal. So whenever you're working on it, make sure that is a normal. We'll see how can we convert or how can we transform while building a model. So scatter plot, what does scatter plot give? We have discussed in the very beginning. It will give you the how they are correlated. How they are correlated. Scatter plot. How they are correlated. See, we have a positive relation in between waist and adipose tissue. But how much can we quantify it? We won't be able to say it. It is positive, but we don't know how much it is. We will be quantifying using the correlation coefficient. We'll be quantifying that using the correlation coefficient. Let's see. So how much we have? The correlation value is 81%. Both are inputs and outputs are correlated. Whenever you have a correlation, it is a strong correlation, right? Whenever R value, that is a correlation coefficient, is greater than 80, then we can say it is strong correlation, right? So we have a strong correlation. Now we can go for model building. Whenever you have a correlation in between input variable and output variable, then only it is possible. Then only it is possible to do the prediction. Then only it will be possible to do the predictions. So covariance, what is the covariance? Whenever there is a variance means spread of data. Variance means spread of the data. All this you will be calling as spread of the data from the mean value. So whenever you are comparing two variables, in that case, we will be calculating the covariance. Here we will be having the positive covariance, that is 639. So in order to apply the linear regression, you can use Escalon matrix, or you can use stats model. You can use any of this and you can go for building up model. You can use stats model and you can use Escalon as well. Simple linear regression. Now we are taking output with respect to input and we are fitting into model. We are imported the start model. When we imported the stats model, and now we are fitting this input and output into the linear regression. See guys, here you got 66.7% R-square value. What does that mean? Whatever the variation that is given by the input, it is not capturing the all. It is not capturing the maximum. Whenever you are doing the regression, you have to check p-value and you have to check whether we have coefficient. You can using this coefficient. What is it? Why is it? B1x plus error. B0 is what? Intercept. That is what? 215. B1, 3 into whatever the x, whatever random value will be taking, you can add that plus error term. Whatever the error term you will get, simply you can calculate the output value. This is the equation that we are getting. That is y is equal to beta naught plus beta 1 x plus error value. You can simply put this intercept and the waste coefficient value, and you can put any input value, whatever the will be having a waste circumference. You can simply put that value and error term, whatever the error term will be getting. We'll see how much error term will be getting. You can input that and you can predict the output. This is the model you'll be having. We'll be having other, we have to look at other as well, p-value, but we'll be discussing in the day. In real class, it is not possible to go through all those things in just 1 hour. So now we are doing the prediction. So we have already built the model. R score is 67% only, since we haven't done any transformation. If you do any transformation, in that case, you can able to increase the value. Hence, here we are using the only base model. So we are simply going through the whatever the value will be having in input, that only we are taking. So we have done the prediction. Predicted value. We'll be getting predicted values are this. Predicted values are this, and the actual values are this. So these are the adipose tissue of actual, and these are the predicted values. Adipose tissue of predict. So there is a huge variance, huge difference. So we haven't done. That is why we got just R square value is equal to 0.67, right? It is less. If it is more than 80%, in that case, you can say strong relation. But we have a less R square value. This is predicted. So this is actual, and this is the predicted value of that R square, or the adipose tissue. That is, we got R square value just 67. So there is that is why we will be having the high difference between the predicted value and actual value. So we'll form a regression line. Where exactly we'll be forming a regression line? Let's see that. So this is the regression line we have formed. And what are the error terms we can assume? These are all. We'll be calculating the distance between all the data points. All the data points will be calculating, and then we are summing all. Root mean square error. Root mean square error. We'll be calculating how much error term will be getting. 32. The root mean square value, how much we are getting? We are getting 32. If you do the transformation, of base circumference or 80, any one of those, and try to build the model again. Do the transformation and build the model again. I'll show you one. You'll see. I am doing the log transformation on x-axis. That is waste column. Input column, I'm waste. I am applying the log transformation on waste column. I am taking y output or y as it is. In that case, we'll see how much correlation we are getting. So this is after transformation. After doing the log transformation, we are getting the correlation like this. How much correlation we are getting after the transformation? We are getting 82. Previously, how much you got? Previously, how much you got? You got 81.8. So there is a slight change. That is how we will be improving model. Each time you have to do changes and then observe the how much difference you are taking. How much difference you are making. And then the same input that we are giving to the model. 80 as it is output, and we are doing the log transformation on input. See how much R square has been improved. Previously we have just 67. Now it is 67.45%. Now it is 67.5%. Do the prediction. You might have gone predicted outputs. That is predicted 2. Predicted 2. check predicted RMSC. Where is it? Okay. Yeah. See, compared to the previous one, it is a bit better. You have less difference compared to the previous one. So like that, you have to do multiple transformation, and you have to keep doing changes, and then you have to go for error calculation. Here, how much? The first entry is good, but the next, how much you got here? RMSE value, it is 32.4. Previously, how much you got? It is 32.7. This small improvement, but it is still, we are making improvement, right? So then you have to do again log transformation on output column, and then again build the model. Log transformation on output column. How much you got now? Correlation. It is increased, right? 84%. And now build the model based on that. 70% improvement. We have R-square value 70%. Then see the predicted value. These are the predicted value. And comes to 3. And you can see the actual. Where we'll be having actual. Duplicate. So these are log values. In that case, you have to convert back to normal. Those are log values. We have to convert back to normal. Comes to regression line. See, this is the regression line. What is the problem here? It's normally not looking like a linear relation. It is kind of curvilinear. So you have to apply the different techniques in order to find the best model fit. This is how you have to do multiple iterations, guys. You have to apply respective transformation technique, and you have to keep increasing model. Keep increasing the R-square value, and you can check. Then what is the error term you are getting? You have to keep decreasing error term, and you have to increase the R-square. If you do something like that, multiple iteration, you will be getting the best fit. Here I'm got a best fit for polynomial transformation. I got a best fit for polynomial transformation. So this is all about the linear regression, guys, and how can we calculate the base circumference. Using the base circumference, how do we calculate the adipose tissue? So yeah, if you want to start a career in data science, guys, this is all about today's class. If you want to start a career in data science, from 11th June, from 11th July, 6:30 to 7:30, we'll be starting Python session. And if you want to kickstart your data science careers, please join our 360Digi YouTube channel, and you can start learning. So yeah, this is all about today, guys. I hope you guys learned something, and we'll see you in the next class, and have a nice day.